Rex Pachinko. This is Obi-Wan Pez. We're going to start just a little bit early here. Alright, I turned the gain down because we had swapped over to our webcam when the headset died, so back up to normal. Hope everybody's having a good week. I've got a few interesting things going on with exams and whatnot coming up, exams that have happened this week. I was just looking through the problem section of a mathematic educator that I found from fall of 2021, so this is last year's edition. Just randomly found it. It's kind of cool though. Yeah. It's weird art. I like it. Anyway, I'm going to start tonight, I think, with talking about some calculus stuff. There we go. So when we start looking at derivatives, the first thing we work on is the definition of how derivatives actually work. And we had mentioned a little while ago that Isaac Newton was very much interested in trying to figure out how to make I guess it's gonna have that angle. How to make the average rate of change, which is going to be determined by the secant of a particular, or the secant line of a particular function. The basic idea was to anchor a particular location here, x comma f at x, and then at some point mark this off and say that this distance here is going to be considered h, whatever that might be. That is going to be a variable distance, so it can come back and forth. The x is going to be overall a variable, but for the moment we're just thinking of it as like a single constant. So the x value at this particular point here is going to be x plus h. Not really surprising. So we go over to x, and then we go a distance of h beyond it, x plus h. And then the y value at that particular point is going to be f of x plus h. So again, same thing. And this is independent of whatever function we have. So doesn't matter whatsoever. Can be anything you want. And the point here is to try to find the slope of the secant that goes through these 2 points. So m bar is often what's labeled, or m secant is going to be equal to f of x plus h minus f of x, because we're looking for the difference between the y values, or the change in y, and we divide by x plus h minus x, the difference in the x's, or the change in x between these two locations. So then up top, this doesn't change anything. It depends on what function it is, because if you have a linear function, then it's going to be pretty easy to show that this is going to collapse into some basically just h, so or a linear multiple of h. And then if we go down here, this is x minus x, so just h. So this is going to be the average rate of change. So our average rate of change, slope of the secant, is going to be our standard slope calculation for any 2 points on a function. You could just list it as y2 minus y1 divided by x2 minus x1. But this is a much more meaningful way to put it, because now we're anchoring a particular x value, wherever that might be, and then we're saying our h value is going to be some distance that goes beyond it. Now it can also go in the negative direction as well. That's perfectly fine. So what Newton found was that if we, in fact, shorten the distance and don't make it this huge h like this, make it a smaller h, I'm going to regret that. There we go. Oh well. It's sad. It's so close to 45 degrees, it just decides that it's going to be 45 degrees. Come on. Shouldn't spend this much time on this. Or whatever. Anyway, move this in, and then find the slope, and then move it in again, and find the slope again. And this was kind of Newton's thing, was be able to take some process and then find its approximation over and over and over again. For successively smaller values, and see what would happen. You could very much visualize all this. We can see that as we start getting closer and closer to the point, our h value is now shrinking down to practically nothing. And this thing here is still f of x plus h minus f of x, our change in y, divided by h, our change in x, which is still getting us the same thing over here. It's just that this is a slightly different h than the other one. So if you wanted to, you could put an h1 on here instead, and then this would be h1 here. But realistically, it doesn't matter. Alright, so Newton said let's do this over and over and over again until we get 2 points that are so close together that we might as well pretty much call them the same thing. So we took this limiting process as h approached 0 of f of x plus h minus f of x all over h. Now the way we do this in class, oftentimes we'll take a function, a particular function, and say, alright, f of x is equal to 6x squared minus 10x minus 3. Right, something like this. So find the slope by limits at x equals 2. So what we do is we say, all right, let's get some bad points for this. We got our x values. We got our f at x values. So at x equals 2, we're going to plug in this, and we get 2 squared is 4, times 6 is 24, minus 2 times 10 is 20, so that's going to be 4, minus 3 is going to be 1. Alright, and this is going to be our anchor point. So the one that's anchored up top here, that we're going to say, okay, that's our x comma f at x, 2 comma 1. And then we take some other point that's sort of nearby. So like, I'm going to go way down here and say this is going to be like 2.2. Now I don't know what that is offhand, so I do have to, generally speaking, grab a calculator for this, because I know it's not that hard. Alright, so 2.2 times equals is 4.84 times 6 is going to be 29.04. Okay, minus 10 times 2.2 is 22. So that's going to be a 7. That's supposed to be a 7. 7.04. Okay, minus 3 is going to be 4.04. Okay, and then we go and say, all right, let's try 2 point. All right, 2.1. It's going to be a 4.41 times 6 is going to be 26.46. Minus 2.1 times 10. So minus a 21 from here is going to be a 5.46. And then minus 3 is going to be a 2.46. All right, 2.01. is going to be a 4.0401 times 6. It's going to be a 24.2406. Minus 10 times whatever we have here is 20.1. So that's going to be a 4.1406. And subtract 3 from that, we get a 1.1406. Blainland, that kind of depends on what we're talking about. So, we're talking, given an angle, or inclined plane, oops, which is totally flat instead of whatever. Okay. I sort of understand that part. So we have an inclined plane that has an angle of theta that's inclined off the ground, naturally. Alright, so there are multiple forces that are going to be working on this particular system. Now we have some sort of block, which can very well be like a thing with wheels, but we prefer to use big blocks because then it has a nice coefficient of friction. Alright, next question. Can I remember any of this? Okay, so the way that we look at this is that we have a force that is enacting on the block, namely gravity, which is pulling down this way. And our force here is going to be m times g. So our force is equal to mass times acceleration. The acceleration in this case is due to gravity, so mg mass times gravity. Okay, then with a force pushing down on the inclined plane, there is a corresponding normal force which it pushes directly away from the plane itself. Ooh, come on now. There we go. mg is gravity. Yep. So this right here is our normal force. And the normal force here has to be... God, man. It's been so long. Has to be equal to the force of gravity, but it's pushing off in the opposite direction. So, again, opposite. It's pushing off the inclined plane. So, in the same way that your force that's being your gravitational force pulled into the planet has to be counteracted by the ground. So, not quite cross product as far as I know, because we're not dealing with a third dimension. So keeping in mind that this here makes a small right triangle, in fact two small right triangles. Right, we got one right triangle there, We got one right triangle there. So let's zoom in on this for a sec. All right, this angle theta here. These are all going to be, okay. So these are all going to be similar triangles to each other. So the big giant triangle that has this as theta, and the right angle is at the bottom of the inclined plane over on the right-hand side, is going to be similar to this right triangle here, which has a right angle here, a theta here, and then our third angle is going to be the complementary, there we go, the complementary angle to theta. And naturally, the same thing happens with the large inclined plane. We have the theta here, we have our right angle down on this side, and then at the top there is going to be the complementary angle to theta. So here, this one ends up being complementary to theta. On the big one, that's going to be complementary to theta. Yeah, a bit. I should break out my Kreyszig book, but unfortunately it's at the moment holding up my screen. Along with my undergrad chemistry book. Alright, and then, by the laws of things that are parallel and perpendicular, let's see. See, this angle drops down like that, which creates, again, our same similar triangle here. So this is a right angle, this is theta, and this is the complement of theta. And this is a right angle here, and this angle here has to be theta. So we're going to have like a series of nested right triangles that all end up being similar to each other. Just the way that they all work out, basically, is just, that's how it's going to be. I know it's a terrible explanation. If we wanted to, right, we could also come up here and look at this and say this here is going to end up being theta. Because if we create a parallel line to our inclined plane, is that going to help? Yeah. Okay. And a parallel line to our base down at the bottom. Then this angle here is going to have to be theta. By vertical angles, this one's also going to be theta. By 180 degrees, it ends up, or by all of our 90-degree pieces, we can work our way over. This is going to be the complement. This is also a right angle because this was normal and this was parallel to the incline. So therefore, this has to be the complement, and this has to be theta. And by vertical angles, this has to be theta. So we could just keep going on with this all the time. Obviously, we don't want to. It's just going to be ridiculous. Probably already is. So our force F equals mg goes down like that. That's going to be the force. The normal force is going to be equal and opposite to the force of gravity, but at an angle rather than 100% in the opposite direction. So without it moving or anything like that. All right. Really? There we go. Okay. This thing here ends up having force equal to. This is where it gets a little fun, right? So the size of this has to be counteracted by the size of this. But the problem is that it's at an angle to each other. Dish, good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are dealing with a physics problem. However, there's an easy answer to yours, and that is that it depends. The best answer. Okay, let's go with magenta here. So this thing here. This thing here has to be literally equal and opposite. But it doesn't actually exist. So we're saying that this is going to get pushed off to the side here because of the inclined plane. It has to be at a right angle to the surface it's sitting on. And so the size then of this vector here is going to deal with the cosine of this angle because it has to do with the adjacent side here and the hypotenuse here. So our force is going to be equal to, this is technically, right, if we think about this in terms of trig, this is going to be that the cosine of theta is going to be equal to F over mg. And therefore, F is going to be equal to mg cosine theta. There we go. And I guess negative if you want to get really technical, but like, it's fine. Most of the time we're just trying to find the size of the force. And so in this particular case, mg cosine theta is just going to get us the actual force that's going against gravity and pushing off against the inclined plane. Yep. So parametric equations. Real quick. So Desh, before we get too far, this was really touching on the concept of limits. So if we get something that's like this, or in fact, we can be much more interesting about this and say, let's say this is x squared plus 7x minus 100 over x squared minus 20x plus 2. No. You don't know L'Hopital's rule yet. I mean, you do, but calc students don't know L'Hopital's rule. Pre-calc students especially don't know L'Hopital's rule. Not to mention, so many people get L'Hopital's rule, and they're like, oh, that's just... You're taking a quotient? You want to take a derivative of a quotient? Sure, just use L'Hopital's rule. Like, no, that doesn't do it. We'll also do some proofs of the derivatives. Sorry, that way. We'll also do some proofs of the derivatives. If there's any downtime tonight. Okay, so here, you look at this and you say, okay, as x goes to infinity, so as x gets really, really big, if we say that x is like 1, then it turns out that, obviously that's not really, really big, but like 1 squared plus 7 times 1 minus 100 is getting affected really strongly by this constant value here. And basically it's driven by the coefficients that are in front of it. Obviously, since it's 1, it literally is the coefficients. So if x is 1, we don't get really interesting thing going on. But if x is like 10, notice what's happening. 10 squared is going to be 100. That directly cancels this thing out. I hate saying that. That directly subtracts this thing out. And then we've got 7 times 10, which is 70. Divided by here, this is going to be 100 again. And then we have a 10. Negative 200, so negative 100 plus 2. So negative 98. So this is going to get us a 70 divided by negative 98. Okay, well, that's kind of interesting. Now that we... Alright, 1 was going to be a negative 92 over 3 is negative 17. Alright, so 10 was going to be a... Forgot already, crap. 70 over... negative 98. Okay, so let's look at 100. 100 squared is going to be 10,000 plus 700 minus 100, so 600. So this is going to be 10,600 divided by 100 squared, again 10,000, minus 2,000, so that's 8,002. Right, so what do we notice about these numbers? This is going to be 92 over 17 is about 5.41. 70 over 98 is going to be 0.71 negative. And 10,600 divided by 8,002 is going to end up being 1.3246. Gets more stuff after that, but nonetheless. Alright, so what happens if we do 10,000? So this is going to be 10 to the 4th. I'm going to start using scientific notation because it's going to get big. So 10 to the 4th squared is going to be 10 to the 8th. So that is 100 million. Plus 7 times 10 to the 4th minus 1 times 10 to the 2nd. So this is going to be a 100 million. This was 7 times 10 to the 4th. Oops, that one. So 70,000. And this is going to be minus 100, so 6, 9, 900. Over. This one is going to be likewise 100 million minus 200,000. That's from here. So this is going to be a 0, 9, 9. 200,000. It's going to be a 7. Okay, that's actually larger than that, so it's 8. 800,000 and 2. So what's this thing? For all practical purposes, it's really close to 1. It's close enough. Oh, I overflowed my calculator. I'm just using a crappy little for function. Where is... There we go. Alright, so 100 million. 69,900 divided by 99,800,002. And we get an approximation. This is going to be 1.002704,388. More stuff after that. So again, if we just look at this and say, what happens as x goes to infinity, becomes really, really super big, then you could say, well, this is going to be infinity over infinity. But we call this indeterminate. So if you just try direct substitution and you get something that is infinity over infinity, 0 divided by 0, let's see, what are the other ones? Infinity minus infinity, infinity raised to the 0 or 0 raised to the infinity. Or no, sorry, 1 raised to the infinity. Then these are all indeterminate forms. We don't know exactly what's going on with them. They could do this, in which case they go to 1. So our limit as x goes to infinity of these two things is actually equal to 1. So x squared plus 7x minus 100 over x squared minus 20x plus 2. Now, you probably knew this anyway, if you've taken pre-calculus already, because you look at the first leading coefficients of polynomials of the same degree. If they're put in ratio with each other, the limit is just the ratio of those two things. Ratio of the two lead coefficients. But why does that work? Well, one explanation is limits. The other one that you could do, right, the driving force behind it is going to be our highest degree terms. So that's why we get A divided by B being the thing that we look for. Alternatively, you could say, okay, I want x squared plus 7x minus 100 divided by x squared minus 20x plus 2, and I could say, let's take all these terms and multiply them by 1 over x squared. And then take the limit as x goes to positive infinity. So up top, we end up getting 1 plus 7 over x minus 100 over x squared. Divided by 1 minus 20 over x plus 200 over x. No, not 200. 2 divided by x squared. And now if we plug infinity in for x, we end up getting these terms, 7 over x, 7 over a really big number, that's going to be 0. So if we plug in infinity, i.e. find the limit as x goes to infinity of these fractional terms, we get zeros for all of them. So 1 plus 0 minus 0 all divided by 1 minus 0 plus 0 is just 1. Okay, so that's one example. We get a value, a finite value. If we stick with polynomials, this actually becomes a bit easier to work with. So alternatively, if we want to find the limit as x goes to 0 of x over x squared plus 1, right, in here, you do direct substitution. You end up with infinity over infinity. And so we say, oh, well, look at that. It must be the same as the previous one, right? So it's just Lie coefficients, 1 over 1. Cool. But that's not it. So in this case, what we've got now is we can actually do the same thing we did up top, where we say, okay, this is going to, if we, I'm just talking too much. If we multiply by 1 over the denominator's highest degree polynomial, and again, just the x terms, the constants can all just stay there, unless something's convenient. Limit as x goes, no, not 0, as x goes to infinity. That's important. Right, this is going to be equal to the limit as x goes to infinity of here, x divided by x squared is going to be 1 over x. Over here, this is going to be 1 plus 1 over x squared. All right, now what happens when we get really, really big numbers plugged into these things? Well, the 1 over x and the 1 over x squared become zeros, effectively. So we end up with a 0 divided by a 1 plus 0. Well, this is now just 0. So what gives with that, right? This is different than the one above. So the one above will become the ratio of the leading coefficients. In the case we had up there, it was 1. If it was something like, 3x squared plus 7 over 2x squared minus 8, like negative 2x squared plus 8, then the limit of this thing as x goes to infinity is going to be 3 divided by negative 2, or just negative 3 halves. However you want to write it. Okay, so that falls under the above case where we get a 1. Well, negative 3 halves really runs the same sort of thing. We have degrees that are equal to each other, numerator and denominator. So that causes us to have the ratio of the leading coefficients as our asymptote. Y equals negative root 3 over y equals negative 3 over 2. I've been doing too much trig, so that's why I get root 3 like all the time. And in this case, right, our denominator has a higher degree polynomial, and when we divide by that thing, it causes the numerator to lose all of its terms and then have only fractional pieces. They all have some sort of x in the denominator, and when x goes to infinity, all those terms are going to go to 0. Okay. So then we go to can be. Do you have a particular problem you're looking at, Blandon? All right, third option, as x goes to infinity, you get something like x squared over x plus 1. All right, so go the other way that we had it from before. We divide out all terms, or multiply all terms by 1 over the highest degree term in the denominator, and it gets us 1 over x. So then this is going to be the limit as x goes to infinity. Here, x squared over x is still x. Divided by 1 over x, or x times 1 over x is going to be 1. and plus 1 over x. All right, as x goes to infinity, we end up getting something that is infinite in extent divided by 1 plus 0. So this is just infinity. So we've got 3 completely different behaviors for infinity divided by infinity. Again, x squared over x plus 1, if we take the limit as x goes to infinity of x squared over x plus 1, and then just do direct substitution, we still get infinity over infinity. It's the same as the other two up above, but when you think about it a little bit more, it turns out that the numerator is going to infinity faster than the denominator. This is where we get something called the hierarchy of functions. So, basically, your natural log function is really slow. And it grows a lot slower, much less than, right? This is talking really about growth and the fact that the values of the natural log of x eventually, as x goes off to infinity, are going to be much less than the values of x raised to... So my other calc book went into like great detail about the hierarchy of functions, and of course that's sitting on my desk at work. Yeah, and I spelled it wrong too. Not hierarchy. Hierarchy. Yeah, there we go. So, our natural log grows really slow, much slower than a root function. So specifically, x raised to the 1 over p, or the pth root of x, whatever it might be, is going to grow pretty slowly. And then we get something that is boo. Yeah, that's alright. We'll leave it there. So we got just x by itself, or x to the first, is going to grow faster than x to the 1 over p. So some sort of xth root. And then after that we have stuff that looks like x natural log x, which grows much slower than some sort of x to the n, or in fact x to any power. It doesn't have to be an integer. Alright, so for values of p that are greater than or equal to, just greater than, that are greater than 1, you get all this stuff here. Alright, that is going to be growing much less fast than an exponential function. So some sort of b to the x, b is going to be greater than 1. Which then grows much slower than an exponential, or a factorial function. So factorial functions are ridiculously fast. I think actually x to the x is bigger than that, but yes, right, Yes, because 10 factorial is 10 times 9 times 8 times 7 times 6, etc., down to 1, whereas x to the x is going to be 10 to the 10th, so it's 10 times 10 times 10 times 10, 10 times. So, yes. Tower functions grow much faster than factorials. So again, when you start talking about growth, really matters what kind of function you're talking about. Alright, and 2.001, we got 1.014006. Okay. So from what we were talking about before, alright, parametric equations. I guess. Alright, so which part, Blamelin? Which part of parametric equations are we talking about? The calculus behind it? So yeah.
The goal of practice is always to keep our beginner's mind.
You hear that?
For a while, you will keep your beginner's mind. But if you continue to practice 1, 2, 3 years or more, although you may improve some, you're liable to lose the limitless meaning of original mind. In the beginner's mind, there is no thought, I have attained something. All self-centered thoughts limit our vast mind. When we have no thought of achievement, no thought of self, we are true beginners.
Okay, so with the plane, are we doing z equals ax plus by? Or is it f of x comma y? So I guess how's it phrased? So you're given an ABC point, right? Or 3 points. Or vectors. No, points. And then find normal vector to the plane containing these points. Something like that. Alright, so let's see how bad I can screw this up. So if we go, alright, so -2, -1, 2. It's going to be here. 4. Ugh. -3. 7. Back there. And C is going to be 1, 5, 1. roughly speaking, something like that. Okay. So there are three obvious vectors that live in this plane. Let's see. There is AB, BC, and AC. Now, we can pick any two of them we want. We can even pick the ones that are going backwards from them. It doesn't really matter. The point is that we're going to take the one we're going to. So B as a vector, it's going to be 4, -3, 7. And we're going to subtract from it A. So A, B as a vector is going to be the vector for 4, -3, 7 subtracted by the vector for A, -2, -1, 2. So we get 4 minus -2, -3 minus a -1, and 7 minus 2 as our vector AB. The taking cup, how's it going? Transitive and substitution. So transitive property says that what you can apply to one relationship and to another relationship. So there's like 4 things interacting. You can also assume that that relationship holds for the very first thing to the very last thing. I'm just gonna flip everybody off. It's fine. So we'll get to that in a minute. Just want to do this real quick. So this is going to be 6. -3 plus 1 is going to be -2. And 7 minus 2 is going to be 5. So that's our vector AB. And why not just do BC? Because, sure. Does it matter? It might matter. Hang on. Yeah, okay. So let's do AC. It might matter. Okay, so A is our -2, -1, 2, which we're again going to subtract from our C vector this time, 1, 5, -1. So 1 minus -2 by 5 minus -1 by -1 minus 2. So that's going to be 1 plus 2 is going to be 3. Wow. 5 plus 1 is going to be 6. And -1 minus 2 is going to be -3. So this is AC. Okay, then the normal vector to this is going to be sticking out of that plane at a right angle to that plane. So no matter where you measure it from on that plane, it's going to be a right angle. So what we do then is we say we want the cross product. This is our normal vector. Is going to be the cross product between I hat, j hat, k hat, and those two vectors that we just found. So 6, negative 2, 5, and 3, 6, negative 3. This has to do with finding the determinants of this whole matrix. So the determinant of this matrix is going to be I hat times the determinant of negative 2, 5, 6, negative 3. Plus I hat times the determinant of 5, negative 3, 6, 3. Plus k hat determinant of 6, negative 2, 3, 6. And yes, I did just do vertical versus horizontal all at the same time. So parametric equations are looking at taking parameters, whatever that might be, and saying, I want this particular variable to be represented by this particular parameter. So for instance, we did this in pre-calc. So we said we wanted to take x, y, and then use t, x, y to represent it. So instead of having one independent and one dependent variable, we went to having one independent variable and two dependent variables. So x needed to be a function of t, and then y needed to also be a function of t. And then this becomes a coupled equation, where these two equations are inextricably linked to each other by whatever t value, t parameter we pick. So they will have this particular relationship depending on what the relationship originally was, or we could just pick one just because we like it. It's going to be 6 minus 30. Yeah, negative 24. Ugh, goodness. Plus j hat multiplied by. This is going to be 15 minus a negative 18, so 15 plus 18 is going to be 33. Plus k hat multiplied by 36 minus negative 6, so 36 and 6 makes 42. So there's your normal vector. Alright, the resource I'm looking at also goes through a nice little derivation of how you can look at V some number, just being an arbitrary point in the plane, x, y, z, and if you take v as a vector, x, y, z, and dot it with n, then you end up getting the equation of the plane. Oops. Not quite. Almost. So I wasn't quite right here. So v is going to be equal to the vector corresponding with arbitrary point minus, really you could use any letter we wanted, but they used A just because. So y minus -1, z minus 2. So this is going to be P, which is just x, y, z minus A. By 33 by 42. I don't think they wanted that as a actual normal either. They just just went with whatever values they got. So dot product of those things ends up being -24 times the quantity x plus 2 by 33, oh no, plus, right, because it's a dot product. Things are waking up now, so plus 33 times y plus 1 plus 42 times z minus 2 equals 0. That's the equation of your plane. Or, well, that's the equation of the plane that goes through those 3 points. We also had, again, the normal vector to the plane that goes through those 3 points, and then the equation of the actual plane. Okay. The taking cup. So oftentimes this will relate to what's called an equivalence relation. And when we get into stuff like abstract algebra, they usually use star as just kind of a catch-all, which means that there's some sort of relationship that exists between these things. Don't know what it is. And in fact, it doesn't really matter because it can be some sort of property that you just don't know about. Like, it can just be a made-up one. So this could be equals could be greater than, could be greater than or equal to, could be less than, could be less than or equal to, or something else.
All right, let's bring that beat back.
So we don't know what it is, but it's an equivalence relation. It shows that there is a relationship between these particular values. So usually it's like A star B. So transitive property specifically says if A star B and B star C, then A star C. So think about this in terms of, for instance, equality, right? If the transitive property holds for real numbers, so if A, B, and C are all real numbers, then we know that if A equals B and B equals C, then we know that A has to be equal to C. Okay, so that same relation has to also hold then for A being greater than B and B being greater than C is going to imply that A has to be greater than C. And likewise, if A is less than B and also B is less than C, that's going to imply that A is less than C. So this is the transitive property. So substitution property is saying that if x equals y now, then x equals y in all relevant relations. And each may replace the other in those relations. So for example, if I let x equal y here, and 5x squared minus 3 y equals 7, then this says that I can have this be instead 5x squared minus 3x equals 7. So we can replace y with x instead and make it an easier problem at some point in the future. All right, there's like a infinite number of examples we could do for substitution property. I do it all the time here because if we want to like exchange a particular look of how something looks, then we can do that in any particular equation. Doesn't matter where it is, doesn't matter pretty much anything at all. We can always be able to change. Can always change the things that we have in the equations for things that make our lives easier. Okay, interesting. So there's also another thing that's going on. So they want to draw a distinction between these two things. Right now I am looking at the Math Giraffe blog, which is mostly a teaching blog about mathematics. So, in this particular case, the person behind Math Giraffe says, here you can actually have both the transitive property and the substitution property depending on how you want to make this work. So in this particular case, this is saying that if we have a plus b equals c, and also that a equals g, then we are allowed, in this particular case, may substitute a for g, or vice versa. Okay, that's substitution. So in this particular case, there is an a over here, which we can then substitute with g instead. Make it g plus b equals c. So again, this is substitution. We've taken a out and removed it and replaced it with g. All right, by contrast, if we take a plus b equals c and also a equals g, and if this were moved around a little bit so that it's a equals c minus b and also a equals g, then we're not removing anything. So in terms of transitivity, two things that are equal to the same thing are also equal to each other. So we're not substituting in this case, but we are saying that, oh look, since we have an a here and an a here, and this is equal to this thing, and this is equal to this thing, that whole thing, then c minus b and g must also be equal. I just cut myself off, didn't I? Yeah, a little bit. It's not bad. Here we go. Yeah, technology can be a bit of a challenge, but technology is only ever supposed to be used as a tool to improve our lives and make things easier, especially taking repetitive or awful tasks that you don't want to do and just being able to automate them. Let the technology do the work. Now, it does sometimes take a little bit of work to ensure that we understand how to use the technology and how to use it appropriately and effectively. But generally speaking, that is the point. It is to make sure that we're taking our tedious tasks and just letting the computer do the work instead of us. Because quite frankly, I would not want to do a table of values like, where'd it go? I would not want to do a table of values like this for 40 terms or something ridiculous like that. Alright, so good. Good evening. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are talking about the substitution and transitive properties for an algebra student. Let me know if you have any particular questions. We can get to your problem hopefully soonish if you have one. Or if you just want to hang out, that's fine too. So, to reiterate, when you're substituting something, you're saying that we have one thing that is equal to another, and then somewhere else when you see that thing, you can replace it with the other thing. So again, A plus B equals C, and also A equals G allows us to say that this A here can be replaced by G. So replace or substitute. Yeah. Oh, cool. Right, was that oh shoot. Yesterday. Selena, oh, that's right, yep. Yep. I've got those in here somewhere. Oh. Yep, she's got her horror emotes out for the month. Love it. Well, welcome, fellow math teacher. What level, if you don't mind me asking? I teach at two-year school and community college on the East Coast. Oh, nice. That was one of my favorite grade levels, possibly just because my teacher was absolutely insane. So, you know, hopefully, hopefully you've got some of that craziness in there. Around the 8th graders, you kind of have to have it. Yeah. Yeah, my you know, post-secondary students, oftentimes I'll do the usual dad jokes or something like that, and they'll just be like, like, come on, guys. But at the same time, we get some really nice high-level talks. So, you know, it kind of depends on where they are in their thingy. So this is true, but you know, the math style dad jokes. Anyway, yep, this is Microsoft Whiteboard. It works most of the time when it doesn't blue screen my entire computer. 3, 2, 1. No, okay. I think I've found that like it blue screens whenever there's some sort of Microsoft update, and so that's when I have to actually like go in and manually do it. It's such a pain. But I am unable to upgrade to Windows 11, and somebody was like, no, you can upgrade to Windows 11, and I was like, okay. All computers, all hardware can do that, and I'm like, uh-huh. So I went in and I found the error code and I threw it up on the channel that they were in Discord, and they were like, I'm still waiting for a response. Like, yep, I told you. It's my hardware. So now I have a tab open on the NZXT website. My wife's gonna kill me. Anyway. So yeah, Microsoft Whiteboard I like. I've been running with a few different ones just because of, you know, pandemic stuff. I started with, let's see, I was doing Microsoft Whiteboard, and then when we went remote, um, I switched to Zoom because, you know, that's where our classes were, and the whiteboard there was just terrible. I couldn't do what I wanted. It was very grainy and, you know, big chunky stuff. And oh, and I was also using a tablet from like, I don't know, 2008 or something like that. So it was a free one that my boss had given me in 2009 and said, just like figure something out with it. You know, go figure it out. You. So I took it and I took it back to my um, office and I let it sit there for like, you know, 6 years. And it wasn't almost until the pandemic started, like a year or something before, that I was like, I could do videos for this. So I pulled it out, and it had like this gunky nastiness all over it. I'm like, so I had to clean it all up. I think it was mostly because the rubber on it basically like melted. Um, and eventually I just got fed up with it, and I was like, nope, that's it, I'm done. And so I ended up getting a very nice new one from Bamboo at my, or not, that's not the company, uh, Wacom. And hope that wasn't important. I ended up getting a nice tablet from Wacom at my own expense, and just like, all right, well, I'm going to use this mostly for my own benefit. So, so I started using that whenever I was at home, and then shuttling it back and forth when I was doing classes. And even the Zoom whiteboard was much better at that point. And having the new Wacom tablet also had a much higher resolution. So the old one was like a, I don't know, 5x7 area. This is basically like, I don't know, 12 by 9, 14 by 11, something like that. I can't even. Yeah, the much higher resolution just makes it so nice. And then Whiteboard also does something nice where, you know, you can start really light, and as you push, it starts making it look like actual, you know, pen strokes. So, yep, that's my ringing endorsement when it isn't causing a blue screen for my stream. I think my video card is not keeping up, which is not surprising because it's like a R7X 260X or something like that. It's really old. So I also do game streams on Friday, and Elite Dangerous is enough to cause it to crash every other program on the entire computer, such that my left monitor, which has my like OBS and monitoring devices and things like that, just completely goes either black or freezes. And then the only thing that'll work is Elite Dangerous until I restart, which is funny because I can also hear, if I'm not actually streaming, I can hear other streams, like the stream that I'm watching on the other screen. Yes. It's bad. But hey, whatever doesn't kill the stream just makes it stronger. We will eventually get some new hardware for this thing, because it's probably due anyway. been about, I don't know, 4 or 5 years since I bought new hardware at all. Oh well. Well, anyway. I was working on some calculus stuff from before. So this is stuff that I've been talking about with my students. None of which is very novel. It's pretty by the book, I would say, even despite my propensity toward inventing some interesting methods here and there. So calc, I haven't done a whole lot of work on that. But if I live in the subject long enough, it'll eventually come to me. Alright, so we were doing slope by limits, where we were comparing the point 2, 1 to all of the other points that were here. So we're doing m secant compared to 2, 1. So this one here, we got 4.04 minus 1 divided by 2.2 minus 2 is going to be a 3.04 divided by 0.2. Alright, which is going to be a 15.2. This one's going to be a 2.46 minus 1 over 2.1 minus 1, which is going to be a 1.46 divided by 0.1, which is going to be 14.6. Okay, this is going to be 1.1406 minus 1 over 2.01 minus 2. Oh, that's a 2 on the bottom. It's going to be a 0.1406 over 0.01, which is going to be a 14.06. And similarly here, 1.014006 minus 1 divided by a 2.001 minus 2. It's going to be a 0.014006 divided by 0.001, which is a 14.006. All right, and we can always attempt more points, but I think at this point we kind of get the point here, is that as we start decreasing the limit variance h to go from, we had a 0.2 difference down to a 0.1 difference, down to a 0.01 difference, down to a 0.001 difference. As we start getting closer and closer and closer to 0, what we end up finding is that this gets closer and closer and closer to 14 with a lot of zeros and then a 6. So realistically, we could say here that probably our slope of the tangent line is going to be 14. So just because it's getting closer and closer and closer, it looks like it. So probably it's going to reach that. Then when we say, okay, let's actually do this out, we can take this function, plug it in, and we say that the limit as h goes to 0 of, this is 6 times the quantity x plus h squared minus 10 times x plus h minus 3 minus quantity, 6x squared minus 10x minus 3, all divided by h. It's going to be limit h goes to 0. I'm going to pull out 1 over h here, and then go further in here. So here we have 6 times the quantity. Well, I don't need to make it so small. 6 times the quantity, x squared plus 2xh plus h squared minus 10x minus 10h minus 3 minus 6x squared plus 10x plus 3. All right. So then here we've got a minus 10x with a plus 10x and a minus 3 with a plus 3. So those are going to be gone. And also we can see here that we have a negative 6x squared, and we're going to have a positive 6x squared. So you can get rid of it now or just wait until you've actually written it out. Depends how strict your teacher is. Mood. So here we have a 6x squared plus 12xh plus h squared. Nope, 6h squared. Minus 10h, not x. Par for the course, really. And then everything else is gone, with the exception of the minus 6x squared, right? Because we didn't get rid of that in this particular section. Okay, so this is equal to the limit as h goes to infinity of 1 over h multiplied by 12xh plus 6h squared minus 10h. Now, if we want to, we can take out the h from the top that is in every term. So we get an h divided by an h, which is just 1, of 12x plus 6h minus 10. Now this is really important. This part here is what's called the difference quotient. And this is what gets you that value from earlier, which we called the average rate of change. Now the difference here is that instead of having 2 specific points that we're using, we go in and we say, I want a specific x value, which is going to get me this point here. And then I want a specific h value, which is going to get me the distance to the next point. So now everything is in terms of x plus your variation or your deviance, h. I suppose deviation would be a better word, not deviance. Everybody's deviant. It's all right. Oi. So x is going to be the point where we're sort of like anchored, and our h value is going to be the variance or difference or distance. So we do distance to our x value. So if we wanted to, we could also replicate all of these numbers that we had over here by saying, okay, if we did the same sort of thing, let's go like this. Okay, and then I'm going to also take out this stuff here. So if we said, okay, so if we said we don't even want f of x anymore, we just want h, which is then going to get us difference quotient values. Right, so this is 0, this is 0.001, this is going to be 2.01, this is going to be 2.1, no, 0. Man. 0.01, 0.1, and 0.2. So again, we're going to anchor this around x equals 2. That's not the right color. If we're going to be accurate, right? So we're going to anchor this around x equals 2. And always use these h values here. Then with an h value of 0.2, we're going to get 12 times 2 plus 6 times 0.2 minus 10. It's going to get us 24 minus 10 plus 1.2. So here, this is going to be 14 plus 1.2. All right, so 15.2, which you'll notice is the same value that we got earlier when we plugged it into the whole equation. This thing allows us to do the average slope much faster for a larger number of potential solutions. So instead of getting f of x for all these things and then plugging it into this particular slope equation, instead we essentially do the slope equation ahead of time and just say, for any values that we're going to do this, let's just figure out what the difference quotient is going to be. And then once you figure out the difference quotient, now you just say, okay, where's our x value that we want to center around, and then what's our h value, the distance away. So here we can also see that this 12 times 2 minus 10 is always going to be here. So 12 times 2 minus 10, which again we can filter that up and just let this be 14. And then here this is going to be plus 6 times our h value, 0.1. So it's 14 plus 0.6, so 14.6, which again, same values we got up here. And then this is 14 plus 6 times 0.01, so 14.06. And then this one's going to be 6 times 0.001. It's going to be 14.006. And then likewise, this one's going to be 14 plus 6 times 0. We don't want a deviation. We want we want h to be 0 in this particular case. So we don't want a deviation from the value we get, 14. Which then, this becomes the really important part. This is the slope of the tangent line, which we already said from above was going to be our limit value here. So we plug in the limit h equals 0, and we end up with 12x minus 10. So the slope of the tangent at any particular point x, or at any particular x value x, is going to get us 12x minus 10 for the slope of the tangent line to that particular parabola. that's the equation up here. So 6x squared minus 10x minus 3. All right, so then in general, we also want to start working on, okay, what kinds of functions do we have? So if f of x is equal to a, it's a constant function, right? This is boring as hell, but we can still do it. And we have to prove this sort of thing anyway. So from the beginning, if you are able to prove what a particular function's derivative is, right, our f prime at x is going to be equal to f of x plus h minus f of x all over h, and that's supposed to be limited, where h is going to go to 0. So f prime at x for this particular function is going to be, well, f of x is a, so f of x plus h is also a. So we get a minus a over h limited to where h is going to go to 0. Well, this is the limit as h approaches 0 of 0 over h. So as long as h is not 0 itself, which was a problem from the beginning anyway, right? We want to know what is the limit value. What are the values that are really close to h equals 0? So again, h equals 0.1, 0.01, 0.0000001. They're all 0. So no matter what we do, we're just going to get 0 for this stuff. So therefore, the derivative of a function like this, d dx of a constant, is equal to 0. Right, which is equal to the f prime at x. We'll also do that. Okay, well then, if f of x equals ax plus b, right, start with a polynomial. Do the linear thing. Then we end up with f prime at x is going to be equal to the limit as h goes to 0 of f of x plus h is going to be a times x plus h plus b minus parentheses ax plus b all over h. So here, same kind of thing we had before. This is going to be ax plus ah plus b minus ax minus b all over h. So ax's are gone here and here. B's are gone here and here. And we're just left with h over h, which is equal to a. So again, the d dx of ax plus b is just going to be equal to a. Can I explain infinite series? That depends. So again, what is it that you mean about that? Like, what is it that you want to have described? No. That's talking about basic derivatives. This is going to be much more, well, could say interesting. I say you meant you. Yeah, it does get rather interesting to make stuff happen. You know, change subjects so fast. All right, so what is it about infinite series that you want to know? Or is it specifically power series? Is it specifically... Oh man, I didn't even put my tags on, did I? Nope. Alright, whatever. Yeah, so it is in effect saying that there is no last term. It's going to keep going on forever and ever. It's just another tool to get used to. So again, it sort of depends on what you mean. If we're talking just like in general, how do we deal with this? Then we're looking at taking some sort of function. That's not what I wanted. Of x sub k. And this is going to say, like, we're going to take f at k sub 0 and add it to f at k sub 1 and add that to, and then keep going until we get f at k sub n, some future value, we don't know what it is, plus dot dot dot, and that's just going to keep going on forever. So if it's literally infinite, this is what's happening. Yes. Yep, and likewise, if it starts with a 1, it's going to start with a 1 term. Alright, give me 1 minute here. Alright, be back in 1 minute. So yeah, I have definitely done I and J, and potentially I and J and K, which again is going to be based on the idea of being able to take multiple integrals. So if you're looking at, you know, stuff that works in higher dimensions, ugh. So you know, thank you. Good enough. So you want to take, if you want to take a chunk out of this, and you were to, like, if there's some sort of variable volume based on a particular function of density. So that's not quite, that's not quite a word. Okay. Then you could do this by a bunch of different means, but you know, typically you're not going to try to find it with x, y, z. You try to find this using spherical coordinates. But the idea here would be that you'd want to take some sort of chunk that is then going to be projected in both X, Y, and Z like that. Like this. Some sort of chunk like this out of a sphere, which would then get you a dr going this way for your radius, a d theta here going with your sweeping angle, and it doesn't really matter which one you do, but a d phi for your azimuth angle. So then here, you'd want to take, again, if you're thinking about this in terms of, my goodness, if you're thinking about this in terms of sums, then you're saying, I want the sum of the sum of the sum of all of the pieces that end up having these particular dimensions. And again, it's going in through all of the sphere, as well as going all the way around this way, as well as going all the way around this way. So here this would be a density function, and your I, your J, and your K will be going from either 0 or 1, it doesn't really matter, to infinity, or rather to n, as our limit is saying n is going to infinity. So this is density sub ijk. So if you take your density function based on your I, your J, your K, and then take a triple sum on each of your, again, delta R, delta theta, and delta phi terms, then eventually this all ends up with a triple integral, as your R goes from 0 to whatever your radius is. So let's just say it's a unit, unit sphere. Your theta goes from 0 to 2 pi, and your phi, and your phi is going to go from negative pi over 2 to pi over 2. Right, azimuth is going to start angled down and then sweep all the way up. Theta is going to cause that to rotate all the way around anyway through all of it. And then your radius is getting all the stuff inside out. Oh yeah. Density, dr, d theta, d phi. I got it backwards now. Right, because you got to start on your way in and then work out. This one's not that bad, all things considered. Right, start inside, work out, like parentheses. Okay. Okay. So, you want to talk about the in general, right? All of the tests that you're going to need for all of your, you're going to look at all of your look up past enrollment, math, number, Spring 22. Alright, there we go. Let me get my divergence, or not just divergence, but let me get all of the infinite series notes. Okay, so that one is super easy. The good news. So for that, you're going to look at that and say, all right, look, if I just take the function itself and let it go to infinity, what's the limit of that thing as n goes to infinity? Ooh. Oh, it doesn't matter. We actually talked about this before from earlier when we were doing the calculus stuff on, this was for the taking cups problem. Right, what's infinity divided by infinity? It depends. Here, if you just do direct substitution, you get infinity over infinity plus 5. So, we don't know. But it's infinity divided by infinity, so it's an indeterminate form. So you could do L'Hopital's rule, but you don't need to. Right, so if you just substitute it, you get infinity over infinity, and it's indeterminate. You can't do it. You are allowed to use L'Hopital's rule in this particular case, because what you're trying to do is trying to find the limit of this function as n goes to infinity. Right? L'Hopital's rule is only allowed when you're trying to find limits. It's the only time you're allowed to use it. What the hell is this? That's all differential equation stuff. Okay. Newton. Separation of variables. Yeah, sequences. There we go. No. Infinity over infinity is indeterminate. We did this earlier. There were 3 distinct behaviors that it could show up as. So, we did that down here. We said that if you had something that had, for instance, polynomials, right? The polynomials make it super easy. If you had something with equal degrees, top and bottom, this gets us a finite number. So, a finite number. If you had something with a larger degree on the denominator, that particular infinity over infinity gets us 0. Nothing else, just 0. Because again, here, the denominator is growing faster than the numerator. And so the bottom becomes humongous, whereas the top is pretty big. So that's getting smaller and smaller and smaller. Whereas down here, if we have a larger degree polynomial on top compared to the bottom, then the opposite is true for what we were saying up here. Our numerator is going to go to infinity a lot faster. So the top will be gigantic when the bottom is just big. So gigantic over big becomes bigger and bigger and bigger. The differences between them are going to become more exaggerated as you go further and further out. So our limit for something that has a larger degree on the numerator is going to be infinity. That will diverge. So with yours, you said if we just take, so our divergence test is that we take the sum of all a sub n as n goes from, I hate doing that, whatever, it's fine. N goes from 0 to infinity, or 1 to infinity, or just any like finite number, because it really doesn't matter. Right? N could be any k value you want to start at, going all the way off to infinity. Right? Usually k is either 0 or 1, take your pick. And realistically, it doesn't matter. You could have it be 20. Right? That's just the first value it picks. It doesn't matter. Okay, so the divergence test is super easy. If the limit as n goes to infinity of a sub n, which are the individual terms of your sequence, if the limit of all those terms is infinity, then the sum of all those values, however many there are, again, there's an infinite number of them, then the sum will diverge. So again, that's going to, like, our sum is equal to infinity. So just having infinity over infinity doesn't tell us anything. What matters is, what do you have for the hierarchy of functions? What kinds of functions do we have in that ratio, in that fraction? If they're of the same type, then we've got to look a little more carefully. If they are of different types, then you can tell immediately what it's going to do. So if you had some crazy thing that was, some x's with a natural log divided by an exponential function, that thing's going to 0, because our exponential function will grow a lot faster than x log x. And again, x log x was in the numerator, b to the x or whatever is going to be in the denominator. So it's going to end up going off to 0. All right, similarly for all these things. If it's on different layers of the hierarchy, you just have to compare them, and that's pretty much it. If it is right, if it's in the same level of hierarchy, then you have to do a little more work to figure stuff out. But it's not going to be horrible. Generally speaking, be pretty good. All right, so divergence test, super easy. If the limit of that function is going to infinity, then the sum of all of those individual terms is going to go off to infinity. It's just whatever it is. Alright, so we got a few different types that we can look at. Alright, so we have a comparison series, or a comparison test. Sorry. You're going to take some particular k goes from 1 to infinity of k over k plus 1. So we want to determine the conversions of this thing. So one of the ways that we can do it is by looking at the individual values that we get out of this. So if we let k equal 0, by the way, we just get 0 over 1, so it's not interesting. We leave that one off, even if this were k equals 0 to infinity. Not really interesting. Alright, so if k equals 1, goodness, we're going to get 1 over 1 plus 1 is going to be 2, plus, if k is 2, then we're going to have 2 divided by 2 plus 1 is 3, so 2/3, plus 3/4, plus 4/5, plus 5/6, plus, etc. Right, but the point is that it just keeps going on forever. And we'd like to say immediately that this is going to be just infinity. But you can't necessarily just know that right off the bat. So in this, we need to do some sort of comparison and say, what are we going to get? Well, this one's actually pretty easy. We can tell, like, this term here is greater than or equal to 1/2. I think you'll agree. This term here is greater than or equal to 1/2. This term here is greater than or equal to 1/2. This term here is greater than or equal to 1/2. This term here is greater than or equal to 1/2, etc. Right, so it turns out that the sequence that we're trying to compare is not arithmetic. It's very different. But what we're saying is that it's bigger than this series, which is arithmetic. Arithmetic in the sense that we're not increasing it at all. It's just going to be a single number. So this series is the sum as k goes from 1 to infinity of 1/2. And here, this is going to be the sum as k goes from 1 to infinity of k over k plus 1. We know that k over k plus 1 is going to be greater than or equal to 1/2 for all values of k greater than or equal to 1. So here, the limit as n goes to infinity of the sum as k goes from 1 to n of just 1/2 is going to be equal to infinity. And so look at these two pieces. So with this one, right, we're saying that infinity divided by infinity is going to be indeterminate. But the limit is not indeterminate. The limit, as this keeps going out forever and ever and ever, is going to get close to a really big number divided by almost itself. So the limit of this term is going to go to 1. So this is a finite limit. Has a finite, the individual function itself has a finite limit. But that doesn't necessarily mean that the sum of all of those values is finite or is infinite. Well, okay. There's a corollary to the divergence test up here. Which is the limit as n goes to infinity of a sub n if the limit as n goes to infinity of a sub n is not 0. Then the sum of all a sub n, and going from 1 to infinity, is going to be infinite in extent. Okay, so based on these two pieces of information, the fact that k over k plus 1 is always greater than or equal to 1/2 for all k values greater than or equal to 1, and for the fact that our infinite sum of 1/2 is going to be infinite in extent, then we can also say, well, this one's going to be bigger. So the sum as k goes from 1 to n of k over k plus 1 is always going to be greater than or equal to the sum of just 1/2 over the same limits. I know where to look them up. Half the problem is that you're also memorizing it. You can't memorize it. It doesn't work. There's too much. The important part is learning the structure. Learn the relationships that exist between these things, and it's much more genuine and interesting knowledge. And the memorization of stuff is interchangeable. You could swap these around and you wouldn't have any clue that you swapped them around. I mean, fine, but at the same time you thought you were going to fail last semester. So the limit as n goes to infinity, the sum k goes from 1 to n of k over k plus 1 is also going to be infinity here. also, why does this work? Well, there are a few different reasons. In general, with a comparison test, what we're going to be doing is we're going to look at taking a particular function oh goodness. No, I got you. All right. So what we're going to be doing is we're going to look at this and we're going to say, okay, this is our series. It's going to be infinite in extent. It's going to continue on forever. Then we're going to look at some other series, which we definitely know what the values are. So our k values, oops, k values are going to be like 1, 2, 3, 4, 5, 6, 7, 8, etc. Right, so this is going to take all those things and make them into what's basically a Riemann sum. And then we're going to have some comparison series. It's going to be like this. Oh my goodness. Alright, whatever. So pretend for a moment that the green one is the comparison series that we know its convergence. So known convergence status. So in this particular case, if we know for a fact that the green function, or the green infinite series, will converge. So if we know that it converges, can we say anything about the black function, the unknown series? Well, let's think. Could it diverge? Well, if the green function, green series, converges, then the black series up here could diverge because the difference between them could be significant, right? It could end up being just like the previous one that we saw, where it could be all a whole bunch of just numbers that you're adding together, going off to infinity. Sorry, just straight numbers like that. So we could add the same number over and over and over again. Could be the case here. Doesn't have to go to 0. Alternatively, it could be, still large-ish numbers that we continually add, and it's not sinking very quickly. It's still going to 0, but very, very slowly. So it could, in theory, still have an infinite value. Could it converge? Maybe. But the problem is that we don't know. So if we have a converge and diverge for the green function, what we're going to want to know is for the black function, can we converge or can we diverge? Based on the information that we have here. Alright, so in this case, we have that forever. Right, we'll call this A sub n and B sub n. So in this particular case, A sub n is going to be less than or potentially equal to B sub n for all n in integers, positive. All right, so if A sub n converges, can B sub n converge? The answer is sure, but it's equally possible it could also diverge. So this doesn't really give us any information. Right? What if A sub n diverges? Right? If it is known that A sub n diverges, is it even possible for B sub n to converge? Well, all of our individual values are larger than something that diverges. So its value at the end needs to be larger, or all of its partial sums, all the sums that go out to n, whatever n is, will always end up being larger than something then that diverges. So here it's not even possible for B sub n to converge if we have A sub n diverging and A sub n is always under B sub n, or equal to. But that means that if A sub n is under B sub n, and A sub n diverges, then B sub n has to diverge. Uniquely, I don't know. It's going to right? If A sub n diverges, then B sub n must diverge. Has to, in this particular arrangement. Right, then all right, then do C sub n. So C sub n is going to be greater than or equal to B sub n for all n in the positive integers. All right, always. So then let's do the same table. B sub n there. C sub n there. All right, if it is known that C sub n diverges, so if C sub n, which is always higher than B sub n, diverges, could B sub n also diverge? Sure, right? You could find something that is going to diverge, but is always slightly less than that thing. Maybe just all of those numbers minus 1. Maybe not minus 1, but like half those numbers, right? If all the numbers are half that one up there, chances are it's still going to diverge if the other one diverges. So sure, right? If C sub n diverges, then C is also going to diverge. Oops, sorry, diverge. If C sub n diverges, can B sub n converge? Sure, right? B sub n could be low enough that if C sub n diverges, then B sub n could be, again, low enough, or a different hierarchy on the function, different function on the hierarchy, that it is going to converge instead. So again, this doesn't really give us any information. So just like with this one over here, if A sub n were to converge, it doesn't give us any information, so we don't care. Just like this over here, if C sub n, the one that's higher, always if we know that C sub n, which is higher, diverges, then we don't really care, because it's not going to give us any information. If C sub n converges, can B sub n diverge? Well, again, B sub n is always smaller than C sub n. So if C sub n converges, how could B sub n diverge? The answer there is it can't. It's not possible. And again, likewise, if C sub n converges, B sub n could also converge. Well, in fact, it has to converge. So this one here shows that B sub n must converge if C sub n converges. All right, so the way I can explain this, I usually use my hands for this. So if you have a C sub n, which is out here and, oops, other way, out here and diverging, it's not really doing anything to B sub n, which is going to be down here the whole time. However, if you have a C sub n, and you have a B sub n under it, then if your C sub n is converging down to a specific value, then it is holding in B sub n. It's going to hold it in and prevent it from escaping, if you will, becoming infinity. It's got to hold it in under a certain value. All right, and then likewise on A sub n, if A sub n is down here and B sub n is higher, if A sub n is convergent, it's holding down, but there's nothing to hold down except itself. If A sub n is divergent, then it is going to take B sub n and force it out to become divergent as well. I don't know if that helps any, but some people like it. So. All right. So an example might be it goes from 1 to infinity of right, 1 over x plus 1 square root of 2x minus 1. All right, I'm going to contend, and you can try out certain values of this, or try adding some numbers, right? Add the individual terms as they go through. I'm going to contend that this converges. So if this converges, then we need a comparison series such that all of our terms, a sub k, must be greater than or equal to 1 over parentheses. Oops, that's supposed to be k's, not x's. All right. Over k plus 1 times the square root of 2k plus 1. And the sum, as k goes from 1 to infinity, of a sub k will converge. So we need something that acts the same way as what we suspect. And then we have to determine, does it need to be higher or lower? Again, if we suspect convergence, then it needs to be higher than this function and hold it back down. If we suspect divergence, it needs to be under our function and it needs to force it out into infinity. So choose a sub k to be equal to, let's see, something that's always going to be greater and we can prove convergence for it by itself. So in order to be greater, its denominator needs to be smaller. So I think we can choose 1 over x root x. Not x, k root k. Alright, so in this case, this is also a sub k is equal to 1 over k to the 3 halves. So we can see the function itself will converge, because this is going to go to 0. But then will the sum converge, because that's going to be slightly different. Alright, I'm going to cheat a little bit and say that I know that this does converge. This will converge by the p-series test. So basically this is just, look at this thing, we got 1 over k to the p, which will converge if p is greater than 1. That's all it takes. Alright, now there is another one that is similarly related to this comparison series, which is going to be the integral test. Which we can use this to prove p-series. So that's why I jumped to this instead. Alright, so one of the things that we had was, is this the... Yeah, it's just the table of values. Alright, never mind. Weird. So in this particular case, we don't want these colors. Alright, so our integral test is going to take all of these points out here. And this is going to be an awful lot like, again, Riemann stuff. So here, this is going to be a continuous function. F of k sub f of x sub k. And then also, we're going to have green. This function here just like we talked about with Riemann sums. This right here, the integral of f of x sub k minus 1 dx is an underestimate of the sum as k goes from 1 to infinity of b sub n. Right, and this is again f of x sub k minus 1. And orange, f of x sub k dx is an overestimate of sum k goes from 1 to infinity of b sub n. if in this particular case we have this function which has an integral f of x sub k dx as x goes from 1 to infinity. If this converges, then b sub n summed up b sub k. This is all b sub k. Damn. Man. Alright, b sub k. B sub k. As k goes from 1 to infinity, will also converge. If the integral from x going from 1 to infinity of f of x sub k minus 1 dx diverges, then the sum as k goes from 1 to infinity of b sub k will also diverge. Now I played a tiny bit of a trick here. These function values are exactly the same. They're just shifted. So it's shifted by a finite amount. So like, all this is really saying is that all you need to do is take the integral and it will have the same behavior as the sum. The integral as, not k, the integral from 1 to infinity of f of x dx must have the same behavior as the sum as k goes from 1 to infinity b sub k. So let me try to explain that again. Our f of x and our f of x sub k and our f of x sub k minus 1 are the same function, just shifted one to the right. Our f of x sub k is shifted one to the right from f of x sub k minus 1. And we just found out that the value of this integral compared to the value of our sum is going to differ by only a finite amount. Because again, we're shifting it over one space. What does that mean? That means in the green one, we're not actually taking account for this rectangle here, but that's it. That's the only thing that we're not actually counting, is this entire rectangle. Which means that the two integrals, which look different, are going to differ by a finite amount, and that finite amount will be the it's not the sum, but it's, sorry, they differ by a finite amount. Because they differ by a finite amount, either the integral has to diverge, in which case we get this one here. If the lower one diverges, then the sum also diverges, the stepping stone one. Well, if the lower one diverges, then so does the top one. It's just shifted by a finite amount. So if it's infinite, then the other one's going to be infinite too. Likewise, if the orange one converges, then the green one must also converge. Because again, they're the same function, it's just shifted over. And we're going to get a little more interesting discussion with what those values would be. But it's pretty much not what we're doing here at all. We're just seeing whether or not something will converge. So, long and the short, right here, the integral of this function must have the same behavior as the thingy. Damn it. Must have the same behavior as the sum of that sequence. So how does that help? All right. You could try and do this one. So we could do an integral test on this thing. The problem with this is we don't have the U substitution. I don't want to do that. However, this one over here is not bad at all. All right, 1 over k to the 3/2 is a doable integral. This is just a power rule. So the integral I'm going to choose the comparison series. F of x is equal to 1 over x to the 3/2. Right. That's our function that we're using, and now let's prove it. So the integral from 1 to infinity of 1 over x to the 3/2 dx is equal to, this is x to the negative 3/2, so when we take the integral, this is going to get us a negative 2/3. Nope, sorry. This is we need the new power. Still got my mind on derivatives. Alright, so the new power is going to be a negative 1/2. So if we divide by negative 1/2, alright, this is what we get, times x to the negative 1/2, evaluated where x goes from 1 to infinity. And again, here we can make this a limit as c goes to infinity of, here this is going to be negative 2, this is going to be c, so the negative 1/2. Okay, minus negative 2, and here 1 just gets plugged in. This is going to be a plus 2, and this is going to be a 0, because here our very large number is being square rooted and also flipping underneath. So very large number at the bottom of the fraction is going to make a 0. So this is going to be 2. So since 1 to infinity of 1 over x to the 3/2 converges, dx. The sum of 1 over k to the 3/2 as k goes from 1 to infinity converges. Alright, so now we know that this thing converges, Oh, come on. Come on. Alright, there we go. This thing converges, and also every term for all k belonging to positive integers, we had that 1 over k plus 1 times the square root of 2k plus 1 needs to be less than or equal to 1 over k to the 3 halves. Alright, so these two things taken together. They show that. The sum, as k goes from 1 to infinity, of parentheses k plus 1 times the square root of 2k plus 1 will converge. Alrighty. Whew. I think that's going to be it for me for the night. So, thank you everybody for coming in. It's been fun. We will definitely be doing more math next week. And Selena is still on her first playthrough of Super Metroid. And with there we go. With Hertz Good coming in and being a math teacher, I think we're going to raid out to Selena. So, thank you very much, everybody, for coming. We will be back next week with some more math, and also on Friday for more game type stuff. So, with that, this is Obi-Wan Pez for NSimpleX Pachinko. Hope you all have a wonderful time, and see you later.